Assalamualaikum warahmatullahi wabarakatuh and salam sejahtera. Okay, today video session we're going to focus on solving problem of handout from the textbook question 6.66. Okay, this is related to our quiz 6 that should be submitted. Okay, the question is regarding if the Earth is regarded a spherical capacitor. Okay, I'm just adding another statement in my quiz, which that we have to solve the problem using Unionist Theorem. Determine the capacitance. So assume the radius of the Earth to be approximately 6,370 kilometers. So that should be the question. And then we're going to solve the question together. Okay, so the question insists that Earth is assumed to be a spherical capacitor. So the first statement that we should ponder is spherical capacitor. Okay, because the question clearly states we need to assume the Earth as a spherical capacitor. So when we talk about capacitor in general, as been defined in my lecture, capacitor should consist of two conductors being isolated by a medium known as dielectric. Okay, that should be our capacitor. With that definition, what we should assume, or we should define our Earth structure should be as shown here. You should have one conductor, which is spherical shape, and then another conductor, which is another spherical shape. That should be the simplest representation of our spherical capacitor. Okay, so this should be our first conductor, this should be our second conductor, and then let's denote that structure to be the inner conductor having radius R1, and the outer conductor is having radius R2, and then let's assume the medium to be free space. So let's say free space between the two conductors. So free space having permittivity epsilon naught. So that should be what we should have regarding the statement given by the question. Earth is a spherical capacitor. Okay, so that's done. Okay, then we go to the second statement by the question. It clearly states, by using Unionist Theorem, okay, so we have to define what's Unionist Theorem. Okay, Unionist Theorem states a solution to an electrostatic problem must obey two conditions, which are original conditions and boundary conditions. So therefore, from our diagram, we must define what is our original and what is our boundary. And then regional, as what we can see, is the region between the two boundaries. So this is what we define as electrostatic problem, consists of region and bounded by boundaries. So therefore, we're going to put a statement here. We're going to assume rho v is equal to 0, meaning that our medium between the two boundaries is free of charge. So therefore, that should be our assumption. And then the second condition need to be define the boundary. So therefore, I'm going to define now at this particular boundary, the potential V is going to be assumed to be equal to 0 because always grounded, whereby the inner boundary having potential V equal to V naught. Okay, this assumption being created in order to agree with the definition that we define regarding Unionist theorem. First, we have to define the region, and then we have to define the boundary. So that's what I'm doing now. Because I want to fulfill the requirement by the question, we need to solve this problem using Unionist theorem. Okay, let's proceed now. So first condition. So I'm going to put a statement here, regional conditions. So that should be our first requirement we need to do when we solve Unionist theorem. Okay, so what we're going to see now, since rho v is equal to 0, therefore we're going to use Laplace equation. Okay, that's what should be our action. So what's Laplace equation? Del square v equal to 0. So now how we solve this Laplace equation? So we have to refer to table, and from the table we need to choose the appropriate equation based on what? Yes, based on the chosen coordinate system, whereby in this problem we have choose the coordinate need to be adopted. Here is spherical. So I'm referring to my textbook now. So I'm going to refer to equation. Yeah? So from page number, okay, so I'm going to refer to my textbook, page number 227. So equations based on spherical now, equation 6.8. Okay, so I'm just referring to my table from the textbook. So what I'm going to see from that equation is quite lengthy. It states here del square v is equal to 1 over r square d over dr r square dv over dr. That should be the first term, plus 1 over r square sine theta. So that should be my theta term, d over d theta, bracket, sine theta dv over d theta. Okay, I'm going to add another term, the phi term here. So what's going to be 1 over r square sine theta square and then d square v over d phi square. Yeah? So that should be our selected equation based on the selected coordinate that we use here, which is spherical. So now I'm going to continue. Okay, in real scenario, in real case, when you work as engineer, you have to solve this problem. Okay, you have to solve this mathematics, and usually the way we do it by using graphical approach, such as numerical method, finite element, finite difference method, or moment that you learn in mathematical engineering. So you have to solve this problem based on that tools. But now based on our syllabus, so we have to simplify. Okay, so see, in our case, our problem only based on one variable situation. So we're going to look into the problem. So from the three variables of spherical coordinate, which are r, theta, and phi, we must decide which one is the appropriate to be chosen in our case. So from the movement of my pen from this point to this point, I can see the dominant variable that I can assume here going to be r variable. Okay, so based on our syllabus now, UTM syllabus. So what I'm saying here, one case variable. Okay, just one case variable now. So I'm going to say now our concluded equation going to be 1 over r square d over dr r square dv over dr will be equal to 0. Okay, there you are. That's how we make it simple, because we just want to show you in our syllabus the process is important. But in real world, when you work as an engineer, you must be more detailed in solving your problem. Okay, so I'm going to continue solving this mathematics. What I'm going to do first, I'm going to move this most left-hand side term to the right part of the equation. So I'm going to have now, I'm going to have 0 multiplied with r square ending with 0. Then I'm going to split my mathematics term here having r square dv over dr should be equal to 0 dr. Okay, then we have to integrate left hand side and right hand side. So by doing that, okay, so I'm going to have now, I'm going to make it to be what here now. So whatever appear in this bracket going to be as it is. So it should be dv over dr. So now I'm going to integrate a constant. So I'm going to have, let's say here, a. I'm going to have a constant a because there's no limit. So you're going to have a constant a as our solution of this integration. Then I'm going to do further by moving this part now to the right. So multiply now becoming divide. Then I'm going to integrate again. So and then I'm going to have this as my solutions. So I'm going to have then by doing the repeating process, I'm going to have here v equal to negative a over r plus b, correct? Because integration of r negative 2 becoming negative 1, you put negative in front and then you add a limit. So this is what we know as general solutions. General solutions. So now I have to go to the second condition of Unionist theorem, which is known as boundary conditions. Okay, for boundary conditions, we just need to define what we can see from the respected boundary. So what I'm saying here, based on our definition of boundary just now, so we said that at r equal to r1, okay, we can see V, the potential is defined by V0. That should be the first boundary condition that we can extract from the diagram. Then at r equal to r2, we can see V here equal to 0. So from there, what we're going to conclude now, so what we can say first, based on our general solution, for the first boundary conditions, we can see V0 equal to minus A over R1 plus B. So let's say this is our equation 1. Okay. And then for the second boundary condition, 0 equal to minus A over R2 plus B. So that should be our second equation. So now what we need to do, we need to solve for the constant A and constant B. So if I'm doing the 1 minus 2 now, equation 1 minus equation 2, what going to be my corresponding solution should be V0, correct? Equal to, I'm going to take the A out. And then I'm going to have 1 over R2 minus 1 over R1, correct? So B going to be cancelled out. So what we're going to end now, so a constant A will be equal to, okay, V naught over 1 over R2 minus 1 over R1. Okay, we have solved for constant A. So now what we need to do for to determine what should be our constant B. And then from 2, okay, so we know that B now is equal to positive. So I'm going to put here V naught over R2, correct? Because there's R2 there, we substitute constant, and then 1 over R2 minus 1 over R1, okay? So we're able to solve for constant A, constant B. Therefore, what we're going to say now, that V will be equal to, I'm going to put the A there, so negative, and then I'm going to put B there, okay, positive. So what I'm going to have now, V naught, okay, I'm going to divide everything with 1 over R2 minus 1 over R1, okay, open bracket. What's going to be 1 over R2 minus 1 over R. Okay, that should be our unique solution. Okay, that's what Unionist theorem define. So meaning that the solution should be unique based on this problem when it obeys original condition and when it obeys boundary condition. So we have done that, but we're not answering the question yet because the question said here, find capacitance. Of the capacitor. So now we need to go to the next step now, solving what should be the capacitance of our earth. So capacitance now, that should be our next step now. So we know that by definitions, okay, capacitance is defined by Q divided by potentials. Okay, that's what should be our capacitance, and based on our diagram now, how we define capacitance. So capacitance, as what we said just now, Q over potentials. So we know that the Q will based on one of the surface charge. So I'm going to say now the Q can be the charge on this surface or the charge on this surface, meaning you can choose either one. So I'm going to say the Q going to be based on what charge reside on this particular surface boundary. Okay, that should be my Q. I'm going to define what should be the Q here, whereby V is the potential difference between these two surfaces. So therefore I can see the V going to be defined as V naught, correct? Because that should be the logical potential difference value between the two surfaces, V naught minus 0, so V naught. That should be the potential difference. So that's done. I just need to find for the Q. So how do I define for the Q now? So I'm going to draw part of my diagram now. So this is my surface. So I'm going to define this to be having radius R1. So this assumed to be conductor, and this is free space. Okay, so we have a condition known as boundary condition between conductor free space. Agreed? And we know when that condition appear, we have to have three conclusions. First, we're going to say the field only appear in the region of free space. There's not going to be any field in the region of conductor. That should be the first characteristic. The second characteristic should be the field will be normal to the surface. Okay, normal. So normal to the surface. And then we know that the third condition will be the charge appear on this particular boundary going to be the magnitude of our field. Okay, so what is this? This is the D. So I'm not sure the direction of the D can be this way or this way, and just put it in general terms. So that's what the three basic characteristics when you dealing with the condition between a conductor free space or conductor dielectric. Okay, there is no going to be any field in the conductor. The field only appear in the medium of free space, and then the field that appear in the free space going to be acting normal to the boundary. And the third characteristic, the charge, surface charge that residing on the boundary going to be the magnitude of the D field. So now I'm going to first find what should be my D now. Okay, so the D have to be related to the V. Okay, so knowing V, I can find the D. Okay, so D going to be known as epsilon naught multiplied with the E. Okay, that should be my D. Electric field density going to be equal to permittivity of free space multiplied with electric field intensity. Then I know that, and the E will be equal to negative grad of V. Okay, that's a standard relationship we used to find electric field from the potentials. And the V should be taken from the solution that we obtained up here. Okay, so I'm going to solve for this E. So using equation, so I'm going to refer to my textbook again. What should be, okay, equation 3.20. This from our Sadiku textbook. Page, let's say you open page 74. So what you're going to see, that grad V equal to dV over dr in all directions plus 1 over r dV over d theta in theta directions, and then finally the last term here plus 1 over r sine theta dV over dphi in the phi directions. That should be taken from the textbook. So now what we need to do, we need to solve the mathematics of E. So therefore my E now equal to negative grad V. I'm going to substitute this term into all the three V in each component, the V here, the V here, and the V here by using this solution we obtained earlier. And you can see for this term, when I substitute, there's no theta here, so the solution going to be ended with 0. Similarly, when I substitute the V in this part of the equation, since our V no phi, therefore the also ending with 0. So I'm going to left with this term only. So I'm going to say now negative. Okay, I'm going to have here D over dr V naught 1 over R1 plus 1, sorry, R2, R2 over R1, and then I'm going to have now 1 over R2 minus 1 over R. What should be our solution then? So remember the R directions. Okay. So differentiation, this term going to end it with 0 because constant. So negative, so becoming differentiate negative R negative 1, negative negative. Okay, I'm going to have negative, and then V naught over R2 1 over R2, R square, sorry, minus 1 over R1, and then R directions, correct? Check again, please. Okay, so r negative 1, when we differentiate r negative 2, the negative must be placed in front, so it's becoming positive. But yet the negative solution, because there's negative term in front here, therefore v naught over r2, then the constant going to be as it is. So that should be our E. Okay, so what we can see now, the E shown here appear to be from outside boundary moving to inside. So this is our E. Okay, based on the solution negative R, or we can also state this is our D. Okay, so now based on our initial, so this is going to be the correct version of our field going into the boundary. Okay, so now that's done. So now I want to find the surface charge. Okay, surface charge density now. At R equal to R1. That's what our objective now. Okay, so we have to use the mentioned equation. Rho S equal to D. Okay, the D should be epsilon not V naught over, okay, now since we want to find the charge at this particular surface, I have to substitute R square now to become R1 square. Okay, because that should be our surface of concern, and then everything as it is, 1 over R2 minus 1 over R1, okay, R directions, dot. What should be my AN now? So AN, as what we have defined in our lecture, should be a unit vector away from your conductor. So this is the conductor medium, and this is the free space medium, the unit vector at the boundary, and must be showing away from the conductor. So since conductor on the left, so the direction should be this direction. So that corresponding to the R, positive R. AN should be stated as positive R, not negative R. So therefore, when you solve the mathematics, it's going to be, okay, epsilon naught V naught over, so I'm going to, because there's a negative here, remember, don't forget about this negative. So I'm going to now change position now. So R1 square still as it is. So now what I'm going to do, 1 over R1 minus 1 over R2. So what I'm doing here, I'm just changing the position of this term in order to eliminate the negative term here. So now it's becoming positive. So therefore, what you're going to have, 1 over R1 minus 1 over R2. That's what the consequence of eliminating the negative. So that should be our rho S. But yet, we want to determine the Q. Okay? So now, we have to go back to this location. And now, what we can say, where the Q now going to be integration of rho S ds, correct? Remember, this refer to these locations. Okay, so now the rho S taken from the soft rho S value earlier, which is here. So that should be our rho S. And now my ds must be substituted with the standard formula for spherical, which is R squared. Since we are focusing here, should be R1 squared. Okay, sine theta d theta d phi. And then remember, should be double integration. Theta from 0 to pi, phi from 0 to 2 pi. And then when we can see here, the R1 can be cancelled out. Yeah? So therefore, what we're going to end here of our our Q should be known as 4 pi epsilon naught V naught over 1 over R1 minus 1 over R2. Okay, that should be the final Q. And then for my capacitor now, we just see the V0 can be cancelled out, should end with 4 pi epsilon naught over 1 over R1 minus 1 over R2 farad. So that should be the capacitance of the general spherical capacitor. But yet we need to adopt to our problem now. Okay, so in our case, when we want to solve the problem, we have to assume now, let R2 located at infinity. Okay, and R1 is given by the radius of our Earth, 6,370 kilometer. Okay, so when you do that, you substitute this value into this particular equation, inshallah you're going to get the solutions. So that's how you solve this problem. So the concern here, we can solve this problem using analytical approach, what have been shown in my lecture when we talk about capacitance. But this problem purposely want this to be solved by using Unionist Theorem. So that's what we are doing now. So what we can see, inshallah, the solution can be validated by using analytical approach, and then inshallah you're going to end with the same answer. Okay, so that's how we verify these solutions. Okay, so alhamdulillah, we have completed solving this quiz 6 problem. And then please remember, on the 2nd of January, we're going to have our test 2. Topic will be involved the latter part of electrostatic that we learned. So test only related to electrostatic topic, because in your final exam, the question only going to be related to magnetostatic and electromagnetic. Okay, so we're not going to ask you again in the final exam a question regarding electrostatic. So electrostatic only will asked in your test. So therefore, test number 2 again going to be related to electrostatic. So hope you're going to do your revisions, and then you're going to do well as well in your test 2. Okay, with that, thank you very much. Assalamu alaikum wa rahmatullahi wa barakatuh.